Thank you all for attending this talk. Thank you, Nico, for allowing me to present. So first of all, just as a disclaimer, I don't usually give lectures. I'm more of a hands-on trainer. So usually I train people for plasma etching and plasma deposition tools on site. But now I have the opportunity to share a little bit of my experience with the RIANA consortium. So as a first presentation, as a first lecture, I'm thinking of introducing people to what plasma is and how we use it in nanotechnology. This is based on my experience with working with students. Usually plasma is a little bit less known in the community unless you actually work with it or study it. So I will give an introduction on plasma, and we will discuss a little bit about the plasma etching tools and plasma etching mechanisms. And in the end, I will present a little bit of some applications that I've been working on and discuss a little bit about the processes and some things that could occur during different processes. So what actually is plasma? So plasma is the fourth state of matter. It's one of the most interesting states of matter to me, because I was shocked to learn that more than 99.9% of the ordinary matter in our universe is actually in the state of plasma. Here on Earth, we are very used to liquids, solids, and gases. We can feel them, we can smell them, we can touch them, but we are not very familiar with plasma. So what is plasma? So lightning bolts, for example, are plasma. The sun, all the stars are plasma. The intergalactic space is a form of plasma. So it can take different forms and shapes. It was first identified in the laboratory in 1879 by Sir William Crookes, and he actually referred to it as a radiant matter. Later on, in the 1920s, a scientist named Irving Langmuir started to actually study this new radiant matter, and he coined the pattern of the name plasma, because in his lab, the first type of plasma he generated was using neon gas. So he basically had this neon gas inside a tube at very low pressure, and he applied DC current between two electrodes, and he actually got the gas glowing. And he realized that this is kind of an ionized gas, and which was glowing red, and he was so fascinated by this color that he associated it with the blood, and then this is where the name plasma came. So basically, what is plasma? For a very layman definition, you can think of what happens if you have an ice cube. So it's a solid, it's an ice cube. If you heat it up, if you give it some energy, soon it will start to melt and turn into a liquid. And if we start to really give some more energy to this liquid and increase the temperature, then it will start to boil and turn to a gas. But what happens if you have the gas and you give it a lot of energy? So what happens is that you start to electrons orbiting the atoms start to leave and start to impact other atoms and give off some energy, and then there starts this cascade effect in which the gas inside starts to get ionized, okay, and you get this new state of matter. And it's a new state of matter because it's completely different to what we actually know. So this medium I like it to call I like to call it a soup because it contains electrons, neutral atoms, different types of molecules, ions. So it's this mixture of different compounds of these atoms or molecules that were inside when you gave them this energy to ionize them. So it's it's quasi-neutral. What this means, quasi-neutral, is it's actually neutral in its entirety from an electrical standpoint, but locally there can be deviations from neutrality. But because um, all these electrons and ions move freely inside the plasma, every time there is a shift and you get a pocket of electrically charged area, positive or negative, it will charge opposite charge, it will attract negative different charges, and it will neutralize itself. So as a whole, this entire medium is quasi-neutral. So as I've said, it contains positive, negative, and neutral particles, and it's an electrically conductive medium. In this figure here, I'm depicting, you know, the first type of plasma generated in Professor Langmuir's lab. It's a simple glass tube which is fed at very low pressures. It's fed neon gas, and you have the positive column, which is glowing red in this case because it's a neon gas, and you have a dark space and then a negative glow. So this dark space is actually rich of electrons, while this negative glow is rich with ions. So you can see the plasma is generating light. So this light which is generated is actually dependent of the type of atoms or molecules that are inside the gas we are exciting. Because when you provide energy to an atom, it might jump to a higher energy state, and when it releases that energy, it releases a photon. And depending on the atom and on the discrete levels of energy associated to the atom, you get different wavelengths of photons released in this process. So plasma, depending on what type of gas, for example, oxygen glows a very nice blue color, while neon is red, and you get different types of elements emitting different types of light. But it is very easy to identify the glow discharge of gases as plasma, but that's not all the plasma types. You have different types of plasma, but this is the most common that we encounter here on Earth and that we use in our technological processes, in nanotechnology. So plasma etching, how do we use this medium to actually etch, to pattern our substrates, our thin films? So as I've said, you have a mixture of different kind of species inside the plasma. So for example, if you can use the ions generated inside the plasma and you can accelerate them towards a substrate, yeah, so ions usually are positive inside the plasma, and if you have a negative bias where your thin film is, you can accelerate the ions towards this thin film, and basically just by ion bombardment or sputtering, as we call it, you can just remove atoms from the film you want to pattern. And this is one of the most basic things you can do. This type of process requires a very high radio frequency power in our tools, very low chamber pressure because you need very long mean-free paths for the ions, so they don't expend energy by collisions with other species. Also, the process is very low selectivity and very low etching rate. What does this low selectivity means? So as you can see in this picture, we have a mask and the film that we want to pattern or to etch. So basically, the ions have no kind of, there's no difference for them what kind of material they impact. And for most of the materials, they will etch at the same rate, no matter what. We usually use as masks, we use polymers, photosensitive polymers, and as films, depends on what you want to etch. Also, anisotropic etching profiles. This give us an anisotropic etching profiles. So an anisotropic etching profile is a profile that is not identical in all directions. As you can see in this picture, because the ions are projected vertically towards perpendicular to the surface, they will usually create these perpendicular trenches. This is one of the methods used typically in ion beam etchers. Chemical etching is the opposite. So instead of using the ions, we use the neutral elements in the plasma or the radicals. The radicals are the neutral elements that are highly excited. And what they do is they just interact with the film we want to pattern, create volatile products, which are then released through inside the plasma or through the vacuum system of the tool. This is in order to achieve such a process, you need a high chamber pressure. So totally different, because we don't want the ions to have any kind of involvement in this process. But having a high chamber pressure also gives you more reactive species inside the plasma, which are able to interact with the substrate. Also, this process is highly selective. This means that being no physical interaction between the species in the plasma and the masking layer or the film that we want to etch is just a purely chemical reaction. So if you have a masking layer which is chemically inert to your plasma components, and your plasma components react only with your substrate or your film, you get a very highly selective process and also a high etching rate. And also this gives us isotropic etching profiles. This means that the etch rate is identical in all directions. As you can see, the etch profile is like a half circle in this case. And reactive ion etching is the third type of etching we use. There are others, but these are the main types of processes that we use. And reactive ion etching is a combination of the chemical etching and the ion bombardment or the sputtering. It basically uses the best of both worlds, but also allows you to control a little bit more the etch profiles, the etch rates, and so on. We will talk more during our examples. So the etching mechanism in a reactive ion etching system is basically inside the plasma, you generate the etchant species. So depending on the film that you have, you need to have the correct chemistry inside your reactor, ignited, and then create the etchant species. Then you have the diffusion to the surface of the etchant species, the absorption in your substrate or film, reaction with the component, the desorption, and creation of volatile products. Then the diffusion into the bulk gas and evacuated through the pumping system. So it's very important that when you select the chemistry for the material you want to etch, the byproducts to be volatile products at the specific conditions you have inside your reactor. This way, you will not have many defects, you will not have deposition of materials. So if your byproducts of your reaction are volatile products, then instead of etching, you might get a deposition process or a growth process inside your plasma system. So a plasma reactor, so basically it's a chamber. You need to have it as sealed as possible. It's connected to a pumping system, and you just have a chamber, a grounded chamber, and an electrode at the bottom on which you place the sample. This is one of the most simplest types of reactors that we use in our labs. They are called a capacitively coupled plasma reactors because it looks like a capacitor. Yeah, so the lower electrode is energized, and it's basically like you know, one plating of a capacitor. Then you have the generated plasma that acts as the second plating of the capacitor. And usually basically by the way that we, uh, apply power to the electrode and make the electrical connections, usually the lower electrode is negatively biased. It is negatively biased because we want to also use the positively charged ions inside the plasma. Okay, so this is the one of the reactive ion etching system we have at IMT Bucharest. It's a Zentech SI 220 system, etch lab system, and with a very nice picture from inside, with an oxygen plasma ignited. And here we have a silicon wafer inside the plasma. Another type of reactors that we use, and they are very widely used in the nanofabrication space, is the ICP reactors, the inductively coupled plasma reactors. So as you can see in this picture, we have here a coil, and we actually use this coil to generate the plasma. And as you can see, there is a second generated connected to the lower electrode. But in this case, for the ICP, we don't use the lower electrode to generate the plasma. We use the lower electrode just to apply a small bias to the lower electrode in order to attract ions. We use the coil to actually generate the plasma, to ignite the plasma inside the chamber. So this gives us a huge advantage, because in the CCP case, depending on the RF power that we apply to the electrode, we also influence the bias of the electrode. But depending on the type of gas we have inside, we need more power to ignite them. So it is directly, the DC bias is directly related to the gas inside the reactor. So it is very difficult to control what the ions are doing inside. And you will see why this is important a little bit later. But for now, you just understand that the ICP is just a system which dissociates, the DC bias from the plasma generation and allows you to create a lot more reactive species inside the plasma without increasing the bias of the lower electrode. So we have two types of etching types we can do inside our plasma systems. So basically you have isotropic etching, as we talked before. So you have the masking layer, and you can see this bowl-shaped etching profile underneath it, and the anisotropic etching, which is basically this almost straight profiles. So let's talk about the CCP plasma and the isotropic etching. And this is a very nice example we've done quite a few years ago. What you can see here is aluminum metal, which is patterned on top of silicon wafers. And then the user wanted to have this central bit suspended above the silicon. So we used a purely isotropic etching, a chemical etching process inside of our reactive ion etching system. So basically you have the reactive ion etching system, but by controlling the parameters inside the plasma, you can promote or negate, the interactions of ions with your substrate, and you can get a perfectly nice isotropic etching of your device. So in this case, we use the Zentech SI 220 etch lab. a flow of SF6 of 100 standard cubic centimeters. So SF6 is the the gas that is mostly used for etching silicon, because fluorine is highly reactive with silicon, at a pressure of about 150 millitorrs, an RF power of about 250 watts, and the etch rate is about 600 nanometers per minute. So this is just for you to have an example of a recipe inside of a reactive ion etching, a CCP reactive ion etching tool for an isotropic etching profile. Also, we can use the plasma to obtain anisotropic etching profiles. So in this case, as you can see here, we do have a flow of SF6 of about 50 cubic centimeters, and we added a flow of oxygen. Also, you can see the pressure is much lower. Here is 2 pascals, about 15 millitorrs instead of 150 millitorrs. And the power is roughly the same, but the etch rate is much lower. But you can clearly see that the profile is quite vertical. In this case, why is it vertical? Well, it's not just ion bombardment. So we could not achieve this etch rate of about 300 nanometers just by sputtering silicon. What we actually did in this case, so we used the 20 SCCM of oxygen, which usually reacts with silicon and creates a very thin silicon oxide layer on the surface. While this layer is formed, ions generated from the plasma bombard the substrate and remove. So we have here the masking layer, and this is the unmasked layer, the free layer, which is going to be etched, and they remove the passivation on top, and then the etching goes down a little bit, and as the etching goes down, oxygen for silicon oxide forms on the side walls, but the ions don't have enough energy to remove the silicon oxide on the side walls. So this side wall is protected, is passivated from the etching of SF6, and the etch process continues down. What you can see here, I put these pictures in there. They're not very pretty, just to show you also some defects. What you can see here, like this very ugly forest, is a residual photoresist. It was not properly removed after the plasma etching, and also these big chunks of dust. They are actually bits of silicon coming off from the wafer when we cleaved the wafer for SEM inspection. So basically, as you can see, these are 2 cases. So the first one is just a purely chemical etching, and the second one is a reactive ion etching process. So it actually allows me to use both the ion bombardment to achieve my goal of creating these vertical profiles, as well as the chemical reaction between the fluorine and the silicon. And I wanted to show you a little bit more details on the side walls. So what you can see here, these vertical ridges, these are artifacts from the photoresist itself. So our CCP system is not very performant, so we know that. And usually we get quite a lot of heat up of the substrates inside the system. So there is an expansion of the photoresist, and this gives us these very ugly ridges, which you can see. And also, maybe you can see here, there is a small slope, and then it goes down vertically. This small slope is a defect. As the photoresist expands, it gets thinner at the edge, and that photoresist is very early removed by at some point it is removed by the ions impacting the surface, and it starts to remove the masking layer on top, and then starts etching over here. So this basically is a masking issue that we have in this case. Okay, so we will go next to the ICP, anisotropic etching. So ICP is very widely used. You can use it instead of CCP very well when we think of etching. But I would like to discuss two cases, two technologies that we have currently in our institute. One is the cryogenic method right here, and the other one is the chopping gas method, or the Bosch process. So for the Bosch process, it's basically you just alternate two gases. First gas is SF6, which is an etchant. You stop the SF6, and then you start another plasma using a gas that creates a thin deposition, a Teflon-like deposition. And it's usually C4F8, this second gas. So you can see there is a deposition, there is an etching here, an isotropic etching, and then you do a deposition. And then when you start the next etching step, due to ion bombardment that you can easily control in ICP systems, you easily remove all the passivation layer, which is on the horizontal substrates, and you can actually perform another etching step. And this usually alternates until you get to your desired depth. This is a room temperature process. On the other side, the cryogenic plasma takes place at cryogenic temperatures, as the name says, at about minus 110 degrees Celsius. What is nice at these cryogenic temperatures, you can use a continuous plasma without the need to alternate between an etching gas and a passivating gas. You can continuously etch, and what happens is that when silicon is exposed to the oxygen and fluorine in the plasma, the oxygen and fluorine instantaneously condense on the surface, creating these oxyfluorosilicates on the surface. And as in the Bosch process, you just remove this passivation from the bottom layer, from the horizontal surfaces by ion bombardment, while the fluorine radicals continue to etch. This is the continuous process. They can be used for different types of processes. The cryogenic process is a little bit more complicated because you need to cool down your chamber a lot. But depending on the application and depending on the end result, these two technologies are complementary. So some examples for the Bosch process. So this is one of the Bosch processes that we typically use in our Plasma Pro 100 from Oxford Instruments. The etch rate is about 2.5 microns per minute. So as you can see, you have two steps that are being repeated as long as you need. And you can actually see for this structure, which I think I think this was a diffraction grating we did in some project. You can actually see this is an etching step, then you stop here, and the next step, and the next step, and you can actually count the numbers of steps you run in a process. So you get this roughness on the sides, but if you do not mind this roughness, you can very usually use this process to etch very high depths with almost perpendicular 90 degrees angles to the substrate. So another example of the Bosch process, we have here two structures that we did in the past. This is an inertial mass, and these are some vibrating structures. So between these two squares here, there is a very, very thin line which vibrates. This is for testing some vibration modes in silicon. And I just wanted to show you this picture. So you have this very thin line, 1.2 microns, which is in between inside this narrow trench. And for the other one, which is coming from this long line here in the inertial mass, you have the same line is roughly the same width, but you can see that this one gets, narrower at the bottom. And these both of these structures come from the same wafer. So you have different behaviors when you're looking at the same structure, the same process, the same wafers, but different behaviors depending on the surroundings. Yeah, okay. So you do not have one process rules them all. you basically, depending on how much exposed area, the loading, as we call it, the local loading, you need to adjust your recipe. You need to adjust a little bit your passivation step and etching step in order to achieve vertical 90 degrees walls. Also, what happens when you have too much passivation? When you have too much passivation, this happens. This is what we call black silicon, because as you look at it, when you take it out of the reaction chamber, the wafer seems black if it's completely covered in these types of structures. So this is black silicon. This happens when you have too much passivation. You do not have an efficient way of removing the passivation. You basically get some etching, and at some point, because of the passivation is not evenly removed from the horizontal surfaces, you start to get some roughness which on the surface, which increases, and those points of roughness actually get more easily coated with passivation layers, and you are not able to remove them anymore during your process. So this is something like that. And this is an extreme case of too much passivation. We actually, as you can see, there is a small etching, but at some point the roughness got so bad that we actually got these types of structures on the bottom of the trench. And at some point, the entire etching is going to be inhibited because there is too much passivation in here. But we actually use this kind of structures. We have used it in some projects with some colleagues of mine doing microfluidics, because silicon is very hydrophobic. You can actually use these types of structures or even these pyramidal shapes to make silicon hydrophilic if you want to do some microfluidics in silicon. So it's not a bad process, but if you can use it accordingly with your application, you can actually use even a defect. Now about a little bit above the cryogenic process. I hope I'm not taking too long. So the cryogenic process is one of my favorites because it allows you a huge range of control over the profiles. And this is an example. So here, as I've talked before, you have oxygen inside your reactor to create these oxyfluorosilicate passivation. And by controlling the temperature and controlling the quantity of oxygen inside your plasma, you can actually very well control the profile of your etching. So you have this example, which is a high quantity of oxygen inside your high concentration of oxygen. Then you adjust the concentration of oxygen. You can get shapes like this. And in the end, if you adjust your recipe accordingly, you can get very, very perpendicular walls and structures. Also, this is a very nice picture for you to see. As you can see, this is the same structure etched in the same process, but these 5-micron openings are just 17.5 microns deep, while this 15-micron opening is like 19 microns deep. So the etch rates that you can obtain in an etching system, the plasma etching system, are highly dependent on the local loading and on the opening of your structure. Okay, so you don't have one recipe fits them all. You have to carefully adjust your recipe by testing, experimentation, and previous experience in order to achieve exactly what you want. And also here you can have this recipe as a test. But we will talk a little bit later. So as you can see, the cryogenic etching is very, very smooth. These vertical lines here actually are not from the etching itself, is again from the photoresist, because in this case we've been using photoresist as a masking layer. And this time, because of the very low temperatures, the photoresist actually contracts, and we again get these structures. But you can also use hard masks in order to improve the roughness of the walls if your application really requires very smooth sidewalls. Talking about very, very smooth sidewalls, this is another case. We've been using, in this case, a hard mask, very thin titanium layers, and we got these very nice pillars. This is for an optical application with very low roughness on the sidewalls. Now, this is just because we've been talking about masking layers. This is something we've been doing in EuroNanoLab, comparing different types of plasma equipment and different types of masks. And this is one of the experiments we've done. So basically, the upper picture and the lower picture you see here, they're the same structure, the same recipe on the same equipment in the same conditions. The only difference is that here we have a photoresist mask, and down here we have, which is a soft mask, and down here we have a hard mask of silicon oxide. But as you can see, the results are very different. And when you use the oxide, you need to compensate because, as I was telling you, you have ion bombardment, which affects the photoresist, and bits of photoresist, which are not volatile in this case, just jump off and add to your passivation here. And that's why when you use the same recipe, you get this notching, because you don't have the extra passivation of bits of photoresist flying around and redepositing on vertical substrates. This is just some fun thing. And another fun thing I wanted to tell you, because I've been giving you some base recipes that we've been using in our processes, is recipe transfer. So if you're planning on using these recipes, you need to know that you cannot use them as are. You can use them as a basis of a starting point, but you need to adjust them to the equipment you're transferring them to. This is an experiment we've been doing in EuroNanoLab, how to transfer recipes from one equipment to the other in different laboratories. So this is, for example, in the left picture, we have a result from IMT using an etch recipe, this exact same recipe used in NTNU in Norway. It's roughly the same, it's not very different. Vertical sidewalls, 90 degrees, 1.85 microns compared to 1.91, so mostly the same. But this is another result from Delft with a similar system, and they got a totally different result. And what we found in this case is that the results that you get when you actually run plasma processes, they are highly dependent on the history of the system and on different setups of the system. So, use a literature result when you're talking about plasma systems and plasma etching. Go online, find papers, get some base recipes that you can use to achieve your processes, but you really need to tune them in order to get these results. I think this is it, just 10 minutes over time. So I hope you enjoyed the presentation.
Thank you very much, Andre. It was quite an interesting talk, quite an interesting overview on plasma etching, on how to use plasma etching for nanofabrication. So please, for all the attendees, if you have questions, just say it to Andre, will answer all of them. Yeah, so Ryan, so please. Sorry. So Ryan, you can say it again, please.
Hello, can you hear me right now?
Yeah.
Yep.
Hi, thank you for the interesting talk. I have a couple of questions, like two questions regarding resolution. So like, I wanted to know roughly how close can you actually etch in terms of, because I see everything that you have here is in micrometers. Can you go down into like maybe tens of nanometers? And then a follow-up question that's related to resolution is that is there not redeposition of the material, especially from the plasma ions hitting the material? Will it not redeposit on the sidewalls, and then you have a tapered profile?
Yeah, that's a good question. So regarding the resolution, basically when you talk about plasma, you can go as low as you want. In our institute, the lowest trenches that we etched were about 10 nanometers. So we built this nanostructures, 10 nanometers spacing with 10 nanometers lines. It really, you can go as low as your photolithography equipment allows you to. If the atom can go inside and chemically react, it will react. It doesn't have a problem. It's not an issue with plasma like it is. It's with wet chemistry. Usually in wet chemistry, if you go below 1 nanometer, you have a lot of problems with surface tension, and actually the chemicals cannot go inside and actually interact with the substrate. In plasma etching, you do not have this issue. The only problem is to have very low pressures if you want to go very small and have the correct chemistry, and also the lithography. And in terms of the redeposition, yeah, that's a big issue. But if you tune your process correctly, usually it's not a huge issue. It's a very huge issue when you use the wrong materials inside your process. So we had, for example, at some point, we had some colleagues that wanted to use some hard masks in a certain types of plasma. And what we found that they actually, because of the sputtering of the hard mask, I cannot remember the exact metal, but I think it was aluminum. So this aluminum was going inside the plasma and actually reacting with the fluorine and oxygen and other compounds there, and redepositing on the substrate and creating these flowers on the substrate. So yeah, you can have some issues, but if you're using the correct chemistries and the correct materials and the correct masking layers, well, it's usually not a process if you can remove them efficiently, if you have the chemistry to remove them efficiently.
Thank you very much. Maria, you have a question? Maria Gonzalez, please.
Yes. Thank you very much for your very nice presentation, Dr. Abraham. And I have a question concerning ceramics. Have you the opportunity to etch ceramics like carbon, silicon carbide, or oxide ceramics like zirconium oxide, for example, which is a very tough one? Thank you.
Actually, I have the same question, Andre. So it's well known that some materials they may require caution prior to plasma etching. So if you can if I can add a supplementary idea to Maria's question, is how, in terms of materials, plasma etching can be used for other types of material, with emphasis also on ceramics, piezoelectric, ferroelectrics.
Okay.
So.
Thanks.
To be entirely honest, we don't do ceramics in IMT, but not because plasma cannot etch them. We do not have the proper tools. And also we have this CCP reactive ion etching, which is good for all. Many types of materials go inside, but it's only a fluorine-based chemistry. And we have the other ICP at the moment too, but it's only for silicon etching. We don't like to, in our ICP reactive ion etcher, we don't like to mix a lot of things, because as you contaminate the reactor over time, the etch parameters will shift, and after a couple of years, you will not get similar results with similar recipes. But I could recommend you from Ilmenau, Professor Christoph Weigel. He has some great work on etching ceramics and hard materials. I think he's one of the pioneers in Europe in these types of processes. And regarding other types of materials, basically, yeah, plasma is like a hammer and everything is a nail. If you cannot etch it because it's chemically inert, you can just pump ions at it and it will just sputter. You just need the right tools for the right materials and also the right chemistries. Right now in IMT Bucharest, we are currently only using fluorine chemistries, so very well for silicon-based materials, silicon nitride, silicon oxides. But we also plan to expand in a couple of years. We plan to purchase some chlorine-based tools in order to allow us to etch different types of metals, to etch 3,5 materials, and also a highly efficient ion beam etcher, which goes for everything else. Of course, when you use ion beam etching, you do have a lot of problems with red deposition, and this is something you need to take care when using this tool, mostly by careful designing of your devices and your layouts.
Thank you very much.
But in my opinion, if right now, if I don't have a chemistry for it, I just ion bombard it and it just goes away.
Okay, so if there are other questions, I have another one. Please, Andrei, if you can answer to this one also, the environmental impact on using different methods of etching materials is a must nowadays. So you have something to add related to plasma etching in terms of environmental impact?
To be entirely honest, right now we at the European level we have this dispute over fluorine gases, especially SF6, which is the primary gas used in the semiconductors industry, because it's a highly greenhouse effect gas. I think is like hundreds times more potent than carbon dioxide, but contrary to the popular belief, in my knowledge from using the clean room and from managing the clean rooms, plasma etching is one of the safest because all the gaseous byproducts you get to neutralize before exiting the atmosphere. So we have special gas filtering systems and actually also plasma cracking systems to allow any kind of non-dissociated gases removed from the reactors to be broken down into components and then be absorbed in the absorbent beds. So it's very clean if you install the appropriate measures to neutralize all your reaction byproducts. And I think it's more cleaner than wet chemistry. I believe it's more difficult to get rid of those nasty chemical stuff. Yeah.
Thank you very much, Andrei. So, other questions? Seems that I don't see any question. Okay. So, Andrei, thank you very much for this very interesting presentation, and I wish to thank also to all the attendees, and please don't forget to send your proposal for future talks to Work Package 5, because all the purpose of all these talks is to promote different line of research within the RIANA networks, within the RIANA community. So looking forward to see your input here. So have a nice day, and Andrei, thank you again. Bye.
Thank you very much. Thank you for the invitation. Bye-bye.